Hello, Ms. Tadros, and welcome to Emil Brill's Advanced Functions Math CCT. Today we'll be looking at page 116, number 5. The height in centimeters of a piston attached to a turning wheel at time t in seconds is modeled by the equation y equals 2 sine 120t. Part A. Select a strategy to solve for the instantaneous rate of change. Part B. Solve for the instantaneous rate of change at t equals 12 seconds. First off, let's establish what we know. We could tell that this is a rate of change question, and more specifically, instantaneous rate of change, also known as IROC. What is IROC? IROC is the measure of the slope of a function at one point. We will be further going into detail on how to calculate the IROC given one point. First, we need to understand that our answer is not accurate. In fact, it's more of an estimate because, well, we're not as smart as those calculus kids yet. Before putting together our strategy, let's focus in on what we're given. We know this is our sinusoidal function. It has an amplitude of 2, b value of 120, so a period of 3. To put these numbers in context, the amplitude is 2 centimeters, and the period is 3 seconds, which means that the vertical axis represents height in centimeters, and the horizontal axis represents time in seconds. It's asking us to select a strategy in order to find the IROC at t equals 12. We're going to start off by choosing 2 points before and after 12. Those will be those 2 circles on the tangent labeled on the graph. Those 2 values are 11.999 and 12.001, both 1/1000ths of a second before and after 12. This will provide us the most accurate IROC. Our third step is substituting those 2 values into the equation of y equals 2 sine 120t. This will result in the y value of our new coordinates. With these new set of coordinates, we're able to solve by substituting them into our slope equation, which will result in our instantaneous rate of change. To conclude part A of our question, outlined is our strategy with very detailed and informative steps. Let's move on to part B of our question. Pay close attention as we execute our strategy derived from part A. We will begin with demonstrating steps 1 through 4 in order to generate our set of coordinates. To recap what we've just done, we have subbed in our 2 values in order to get our set of coordinates. These set of coordinates are outlined on the tangent line. To conclude the final 2 steps of our strategy, we must now solve for the slope, which will result in our instantaneous rate of change at t equals 12. Before calculating the slope, we need to understand the formula. M is equal to y2 minus y1 divided by x2 minus x1. That is why we need to come up with our set of coordinates, as we have labeled here. As we have demonstrated through steps 4 to 6 of our strategy, the instantaneous rate of change of the piston on the turning wheel at 12 seconds is at an increase of 4.19 centimeters per second. This means that at the exact point of 12 seconds, the piston is increasing at a rate of 4.19 centimeters per second. In fact, rate of change is so commonly used and so important that I can relate it to many important careers, as well as things that I even do every single day. Rate of change can be applied to airplanes as well as flight paths. Rate of change is also used in the marine life industry. And of course, rate of change is used in business, stocks, and money. Virtually everything in every career you know uses rate of change. For example, looking back at airplanes, then changes in speed or altitude over a period of time is modeled through rate of change. Even IROC, the speed or the altitude at that particular moment. Looking at marine life, you can graph the population change over 10 years and determine what the rate of change is. And most importantly, stocks, the percentage change at that particular moment or the lifespan of the company. Rate of change is a very important tool and it's used in almost every single industry. Now that we've explored rate of change in the world of careers and industry, let's briefly recap how we used it for our piston on the turning wheel. We generated two sets of coordinates using our strategy so that we could solve for the slope at 12 seconds, resulting in our instantaneous rate of change. Thanks for watching, and I hope now you're ready to solve the IROC for all the pistons that you ever encounter on a turning wheel.